Okay, welcome to Advanced NMR Spectroscopy course. So today I'll start. The topic is NMR of dynamic processes. So before we go to that, we'll just okay. So before we go to that, we'll just remind you, because this I have already in my earlier lecture, one of the lecture, that how you detect the signals in NMR. Okay, so in a rotating frame, how we detect. Okay, so in the, what we have seen in the rotating frame, that we keep the radio frequency. The frequency of the radio frequency is same as the rotating frame frequency. And B1, the radio frequency field is applied along the x prime axis. The rotating frame x axis is called x prime axis, and detector in the y prime axis. Okay. So now we are not talking about any pulse NMR. So spins, those who are having the frequency, let us say this. So if you see the spins having the frequency omega 0, which is coming due to the applied magnetic field B0, and when it matches with the rotating frame frequency or the radio frequency, or we will call the transmitter frequency, so then they undergo a phase coherence, and the magnetization due to these spins tilted from the z prime axis towards the y axis, that we know. So automatically you now your magnetization due to those nuclei are in the xy plane, and you can detect them. Okay, and that is done. The how the signal and all these things will look like is can be derived using the called block equations. Okay. So block as having several equations in x axis, x prime axis also, y prime axis also, z prime axis also. Typically, we will be dealing with the y prime axis, because we have kept the detector there. And if you see the block equation, so this is the rate of change of y prime axis magnetization with time is given by this. This omega 0 is the precessional frequency, and omega is the frequency of the radio frequency wave or a radio wave, and this is the magnetization along the x prime axis. See, when the magnetization come to xy plane, you will get the magnetization both in the, you can detect magnetization in the x axis also, y axis also, but not in z axis. Okay, so that's why you will see that this x prime is also there, and this is nothing but the gyromagnetic ratio. This is the B1 magnetic field strength, and this is the magnetization along the z axis, the mz, and this is your magnetization along the y axis, and this is, you know, that the relaxation time or time constant T2. Okay. And if you do all the mathematical processing, so the from block equation you get the value of magnetization along the y prime axis where the detector is there. So that if you do all this, I have not shown these calculations. You can get it in the book of Gunther. If you see it, go to the appendix, you will see all these equations. Okay, and their solutions. So this is the final solution of that. My prime is equal to this is related to your m0. You can consider that this is your the gyromagnetic ratio, the B1, and then T2. All these things we have already discussed many times. Okay, so m0 is the equilibrium magnetization. Okay, under the applied field B0 along the z prime axis, gamma is the gyromagnetic ratio, omega is the Larmor frequency of the nuclei under the applied field B0. And then I told the omega is the frequency of the varying radio frequency field of field strength B1. Okay. Of course, this field strength also you have to express in Tesla unit only, because B0 also we are considering in Tesla unit. So you have to use the Tesla unit. And T1, T2 are the respective relaxation times. Okay. So see, this will not be doing any mathematical calculation, but I told you how the signal intensity नाइजर का कोई आया नहीं है। देखो दोनों में देख लो कनेक्टेड हुआ है क्या नहीं। Okay, so what I mean to say that whatever is happening, we are getting the average spectrum because all these physical processes, whatever is happening, the conformational change and orientations of the molecule, they are much faster with respect to the NMR times. So the signals which So what the signals you see in your NMR spectrum is that like chemical shifts. So you get the chemical shift, all weighted average of all possible conformation. Similarly, the coupling constants also. See, when there is a change in the conformation, the coupling constants also change, because if you remember the Karplus equation or all those things, you will see they are angle dependent. So when there is a rotation around a single bond, the dihedral angle changes. The coupling constants also change. So coupling constants are also averaged from all possible conformations. And also the relaxation time constants, the T1 and T2, they are also depends on the conformation. Okay. So that means all these NMR parameters get averaged out due to the as the process are very fast with respect to NMR time scale. Okay. Now let us consider a case. This is a just case. Let us say ethanol. Ethanol is binding to a receptor and then dissociate again. Okay. Okay. So assume you have a receptor which is having a, let us say, some aromatic group here. Okay. So the ethanol is interacting in a hydrophobic manner. That's why it is a, you may ask you why it is approaching this way. That's why I have drawn a benzene ring here. So it is a hydrophobic interaction. Okay, and this is where there is no complexation. So there are two scenarios. One is that it is bonded to the receptor, another is the non-bonded. So when it is bonded, you can see that this methyl group comes close to this anisotropic benzene ring. So because of this anisotropic effect, the chemical shifts, it gets uphill shifted. Okay, and whereas here it is just normal chemical shift. Okay, so the methyl group, you see that it has got different chemical environments in the bound and the unbound state. Okay, and I told you why we are considering the chemical shift is uphill shift is because of the way we have chosen. This is a just arbitrary. Suppose you have a functional group here, a carboxylic acid group, you will see the CH2 is interacting. Then you will see the CH2 will be having different chemical shift. Okay. Now let us see. Now depending on the exchange kinetics, okay. Now if the methyl signal will either appear as a single, so if it is a very fast, this exchange is happening very fast, then you will see only a single peak, okay, which is average, again weighted average of these two fractions. So how much fraction of ethanol is here, and how much is automatically, it will be 1 minus F1. Okay, so you will get the chemical shift will be like that, F1 into delta of this plus 1 minus F1 into delta of complex, this is delta 3. Okay, so you will get the chemical shift if it is if the process is very fast. Okay, so but if the process is slow, you will see that you will see a peak due to this methyl, which will come at, you will see one peak is coming at 0.5 ppm. Let us say this is 0.5 ppm, this is 0, and then you will see it as at 1 ppm. So you are getting this, and let us say you are getting the time being, I am neglecting the coupling of with the CH2. Okay? Assume that there is no coupling. Okay, so but see, as you will see, I have shown you a peak here where the free, this is at 1.0. So your free ethanol amount is more. If you do the integration, you will see this is small. Let's say you will see this is about 80%. This is 20%. Okay? So you will get two peaks, one at 1 ppm, another at 0.5 ppm, with relative intensity of 8:2 or 1:4. Okay, if this is the thing, it can be anything, just arbitrary. Okay, it can be 1:1 also. It can be other way around, 90% is bonded, 10% is free. Okay, so one can tell from the so you'll get two peaks and you can integrate them and you can tell how much is bound, how much is unbound. Okay, still they are exchanging, but now the exchange rate is slow with respect to NMR time scale. Again, we will tell what is how What decides that, whether it is a fast or slow? We'll come to that. Okay. So now you have three possibilities. One thing is the slow exchange, as I told you, you will get two peaks. Okay. Two sets of resonance set with reasonable sharp lines. Okay. When they are slow. Then another will be the fast exchange. I told you you will get only one line, one signal. Okay, which is again the average of this and this. Okay, with the factor of what is their relative ratios. Okay, and there is a possibility to the intermediate exchange. Okay, what you will get a very single and a single line with a very broad. Or sometimes you may not be able to see it because it is so broad that it remains in the baseline. So to predict the appearance of a spectrum of a molecule undergoing dynamic reversible exchange, three parameters should be known. Okay. So if you want to predict how the spectrum will look like if the molecule is undergoing a dynamic reversible change, so what are those three parameters? First thing is that you should know their chemical shifts. Okay. So of course, chemical shift we'll take that value in Hertz. Okay. And then the other parameter is the coupling constant. That is also in Hertz. Okay. Okay. And if you know that, you will be able to find out what is the chemical shift difference. The delta nu zero is nothing but nu A minus nu B. Okay. So first thing is that you should know the chemical shift. Okay. So you can get that value with respect to, let us say, TMS, some Hertz. Okay. Then second thing is the population. As I told you in this case, 80 is your unbound, 20 is bound. So that is called the population. Okay. So that you will be able to get it by signal integration. Okay. The population of the exchanging structures. Okay. And then the rate constant for the interconversion. What is the rate? Because that is whether it is slow, whether it is fast, or whether it is intermediate. Now let us come to the next slide. So that is it. See, if you see the previous case, it is a ethanol and bound to this a receptor site and unbound to receptor site. So, but see, there is a possibility that it could be 100% bound, it could be partially bound. So ratio is, you cannot tell. But so we should take a system where we know that both the things will be 50-50. Okay, so there is no chance that it will be different. Okay, so I have taken one example, and this is the first example where this dynamic NMR has been introduced into the NMR. Okay, so now I will try to give a quantitative picture about the dynamic NMR. Okay, so we will take this example and then go ahead. Okay, so now you know this DMA. This is the structure of DMA. And those who are from organic chemistry, you know this nitrogen lone pair actually makes this carbon-nitrogen bond somewhere double bond character. Okay, so this is the resonance form of DMA. So that's why you will see it will be having two conformers possible. And sorry, so these two conformations are in equilibrium. Yes, they are conformers. They are in equilibrium. Okay, but they are, and if you see now that this methyl and in this methyl, they are not same. This methyl is there is a anisotropic interaction between this carbonyl and this methyl. So that will be different. So this methyl will have a different chemical shift compared to this. Okay. Now due to rotation, so okay, so there will be change in the position. Okay, so this methyl now will go to this position. So nu A and nu B will be changing their positions. Okay, now let us say consider the rate is, we know that this barrier of this rotation is about 20 kilocalorie per mole at room temperature. That's a very huge barrier. That means the rate you can find out what should be the rate constant, and you will see that it is a very slow. So that's why the two methyls, they come in clearly two peaks. Okay, but now if you increase the temperature, so what you are doing by increasing the temperature means you are increasing the rate of interconversion. So what you will see initially, you see there is a change in the broadening of the peak, then they will finally broaden very much, and then you will see there will be a broad single, and then finally at very high temperature above greater than 120 degree, again you will get a single peak. So now again both the things are there, but now they are exchanging very fast. The rate is very fast. Okay. So that is called the lifetime. So if the lifetime is nothing but it is 1 by rate constant of the nuclei in each site is sufficiently long, they will appear at different position. Okay. Now, so what is the lower limit? So that you will be able to see the signals. So the lower limit of the lifetime of two signals is given by tau delta nu is equal to 1 by 2 by. It is nothing, it is coming from your uncertainty principle. Okay, so if your tau is smaller than this, you will get one line. If it is more than this, you will have two lines or broad lines. Okay, so and delta nu I have told you already, it is the chemical sheet difference. Okay, so that's why if tau becomes too small, a time average spectrum is observed, and that is the thing so far we have seen. We have seen a time average spectrum because the lifetime of a particular conformation is very short in most of the NMR's spectra we have discussed. Okay. Now let us come to a general dynamic. So this is the dynamic process, A to B again. Okay. So the chemical shift value is nu A for A, nu B for B, and these are the respective rate constant. K from A to B and B to A is Kb. Okay. So now if you want to find out the quantity relationship between the line shape of the NMR signal and lifetime of the protons in both the position, you have to use the modified block equation. That's why I told you the block equation. Okay, but anyway, we are not going to do all the calculation. Ultimately, whatever final equation is derived from the block equation. Okay. Now let us see what are the things you have to consider when you want to modify the block equation. Okay. Now if you see the signals at nu A or nu B, okay, they will be modified not only by the relaxation effects. You must remember that all we know the signals A and B point when there is no equilibrium or there is no this thing, let us say there is no exchange, you will see that it will solely depend only on the relaxation effects. Okay, but in this particular case, it is not only the relaxation effect, but also there you will see a time dependent change of the magnetization at each site caused by the chemical equilibrium. So that part I clearly have told you. So let us say let the site A. So MA is so okay. So you will see that the magnetization for the site A is increased, okay, by an amount proportional to the KBMB, because this KB is getting converted to A. So that is also increasing your signal strength. So that is increased, and you will have there will be a decrease because that will be your KA into MA. So your MA is getting decreased due to this forward reaction, and it is increased due to the backward reaction. Okay, so you have to consider both of them. The Ka and Kb may not be same. If they are equal, then there will not be much difference. But if they may be there, many times you will see they will be different. Okay, in case of dimethyl formamide, it was Ka is equal to Kb, but in general you will not see that it is always it has to. Okay. Similarly, the MB for the site B will be similarly, it will be increased by a proportional to KMA and decreased by KBMB. Okay. Now, if you now consider those things and apply those things in the block equation, you will get finally the line shape equation of the NMR signal. Okay, I am not going to. So this, if you those who are interested, you can see the appendix of this Gunther book. Okay, it is given there. So what is the line shape equation? This is nothing but the intensity of signal. You can call this is a intensity of signal. okay, is equal to G nu is equal to 1 plus tau. So you will see this tau is nothing, again tau is a reduced lifetime, okay. It is tau is equal to tau A, tau B divided by tau A plus tau B, where tau A and tau B are the average lifetime of nuclei A and B, okay. So that is your now tau, and this delta. Now delta is the width at half height of the signal in the absence of exchange. Okay, so that means lifetime is infinity. Okay, and that will be equal to, this is the natural line width, I mean to say. Okay, it is the natural line width of natural NMR line width. Okay, approximately let us say around 1 hertz. Now we have the this nu is that is the variable frequency where for what you are trying to find out the line set, okay. So that is your variable frequency because that is changing. Now delta nu is the nu A minus nu B. It is the difference in resonance frequencies of nuclei at position A and B, okay. So this is nothing but this, okay. Their chemical state is the difference, okay. Now this P is again, now this P is elaborated. What is P? Okay, so it is a very big equation. That's why there are again putting P, and then again I am explaining P. What is P? So P is again 0.25 delta square minus nu square plus 0.25 del nu square into tau plus del by 4 pi. Similarly, there is one term QR. So Q is again minus nu minus 0.5 Pa minus Pb. Pa and Pb are nothing but they are the molar fractions of A and B. For DMF, it is 1:1. Okay, so 0.5, 0.5 in case of DMF. Okay, but other cases it would be different depending on the equilibrium position. Okay, and then R is also it is 0.5 Pa minus Pb del nu minus nu. So all these things are there. Okay, so this is your final equation, and now if you now you can simulate NMR spectra. Okay, you can simulate NMR spectra using this equation by putting all those parameters for a particular compound, and what you will see that so in this particular case, what spectrum I have shown here, I have taken tau A is equal to 1 by K. Tau A is already 1 by K, tau B is equal to 1 by KB, and then this del nu is equal to 30 hertz. That means the difference between these two is 30 hertz. Okay, and then as I told you, now PA and PB, that's why you can see the peak intensities are equal. Okay, so PA is equal to PB is equal to 0.5, and delta, the capital, the line shape, the line width, natural line width is taken as 1.0 hertz. Okay, now depending on this tau A, okay, and tau B, you will have the tau value. Okay, now let us say the tau is very large, so that we will call as a slow exchange region, okay, or slow exchange regime. Then what you will see in the slow exchange regime, you will see the nu A and nu B are appearing separately. But as you reduce the lifetime, see this is for let us say tau is equal to 1 second. Now you reduce it to 0.5. Okay, you see that still they are separate. Now I see there is a change in the light width. Okay, the lines are becoming broader. So similarly, up to this, you can see up to this, this is called the slow exchange because you can still see the two peaks. You can see, okay, and then a regime comes where you will see that you will not be able to see clearly to see two peaks. It is called the intermediate exchange. Okay, so this is called the coalescence of peaks. Okay, and then beyond that is the fast exchange. Initially you see the broad line, and then finally when it is very fast, you will see again the natural line with the delta. Okay, here also it is delta, here is also delta. Okay, so for slow you will see the peaks are coming separately. When intermediate you will see a very broad peak, and when it is very fast, you will see a average peak. Okay. This is not only the chemical shift, there are other parameters. So if you see that in case of fast exchange, okay, in this particular case, okay, this NMR parameter, here I am talking about the delta value, okay, it is the weighted average value of all contributed from all possible components. Okay, same thing I have told many times. So P will be summation of Pi. Pi is nothing but the mole fraction, and this Pi is the parameter value for that ith component. Okay, so here only two components. If it is equal, it will be just average of this, average of nu A plus nu B by 2. So this position will be nu, this delta will be equal to nu A plus nu B by 2, because here EA plus EA is equal to PB. Okay, but if PA is not equal to PP, then you will see that this will not, you may not see exactly at the center. Either the peak will be this side, slightly this side. We'll see one example, such example. Okay. Okay, now the most important thing is the NMR time scale. Okay, again the same dynamic equation I have told, and lifetime also I have already discussed. Okay, so now I have also told that this NMR3, the NMR parameters that characterize both states are the chemical shift, scalar coupling, and the line width. Okay. Now see, this is a very important thing. You must remember the NMR time scale is defined by the relation of the exchange rate. Okay. So there is a relation of the exchange rate. It is nothing but the rate constant with respect to the magnitude of the accompanying change in the corresponding NMR parameter. So this corresponding NMR parameter could be chemical shift, it could be spin-spin coupling, it could be the line. So what you are observing is very important. So for that you have to see the NMR time scale. So you have to, so automatically the time scale for chemical shift will not be same for the scalar coupling or for the transverse relaxation or T2. Okay. So for example, let us say, so these are called the exchange rates. So you can have now three, that is called the time scale. One is called slow, intermediate, and fast. So when you will say it is a slow time scale with respect to chemical shift, we will say that if the rate constant is much less than the delta nu, then we call this a slow. Okay. If the rate constant is more or less equal to the delta nu, we call this as an intermediate. And if the rate constant is much more than the delta nu, we call fast. Okay, and that is the only we have seen with the conformational changes. Our rate constants are very high, 10 to the power 9 per second. Okay, so they are very high. See, let us say if you see the axial and equatorial proton of cyclohexane, you will see that del nu is about let us say 20 hertz. Okay, whereas your the K is 10 to the power 9. So if you compare this 20 and 10 to the power 9, it's very fast. So that's why you do, normally you axial equatorial proton of cyclohexane you see as a 1p. But if you reduce this conformational change rate, you will see that they are coming separately. You will see that. Okay. Now for same thing, if you are observing the scalar coupling, then you take the we'll call this is a slow if the coupling constant difference is much greater than the rate constant. Okay, so coupling constant difference is also in hertz. Okay, if they are very close to that, it is intermediate, and if it is the rate is much faster, we will call this is a fast. Okay, similarly the transverse relaxation also K, if it is slow, then 1 by T2A minus 1 by T2B will be much greater than the rate constant. If it is intermediate, they will be almost equal, and if it is fast, the rate constant will be much more than the 1 by T2A minus 1 by T2B. So this is a very important thing. You have to remember what is NMR time scale. So NMR time scale is not, suppose you are getting a NMR time scale slow for chemical strip, does not mean that it will be slow for scalar coupling, or it is for transverse relapse. Okay. Okay. So it depends on these values. You see, these values decides if the chemical strip values are much different. Okay. So the delta nu will be much larger. Whereas J and J does not change much. Okay. So these are the things you have to remember. Okay, now let us see the exchange time scale is again I have shown this thing in a different way. So the exchange time scale is defined by the separation of the two signals relative to the exchange rate. Okay, same thing I told in the previous slide. Okay, so this ratio is influenced. Now one parameter is the temperature. Let us say if you change the temperature, what will happen? It will accelerate the exchange reaction and therefore pushes the system to the fast exchange regime. So let us say like DMA, if you record the NMR room temperature, you will get 2 methyls. But if you go to 120 degree and above, you will see only 1P. So by increasing the temperature, you are pushing the reaction from a slow exchange regime to fast exchange regime. Okay, it is not that all reactions are slow. Similarly, let us say cyclohexane case, axial equatorial. If you cool it to very low temperature, you will see the axial equatorial protons are coming separately. So they are also by cooling, you are pushing the fast exchange regime into the slow exchange regime. So temperature is a parameter. So if you see, if you increase the temperature, your slow exchange regime is going to fast exchange regime. Now let us see, there is one more very important parameter is the magnetic field. So that's why when we are doing this experiment, this dynamic NMR experiments, so in all machine you will not get the same result. Okay, suppose if you are recording the NMR, dynamic NMR in 60 megahertz and you are doing in 500 megahertz, they will be totally different. See, why it is happening? So let us say two protons are separated by 1 ppm, one delta is equal to 1 ppm. In 60 megahertz, it is 60 hertz. In 60 hertz, in 60 megahertz, it is 600 hertz. Sorry, this is 300 hertz. 300 hertz in 500 megahertz. No, I'll put 600 megahertz, so it will be 10 times. So this will be 600 hertz. So it will be just 6 times. So you see, your delta has now increased. Okay, it has now increased. So automatically, if your now your denominator, the numerator has increased. So it is between the numerator and denominator. Okay, your exchange rate is same, but you have changed the numerator. So by this way also you are pushing the fast exchange regime to slow exchange regime. So if you record a spectra, let us say in a lower frequency machine, you will get a fast exchange. You record the same spectra in a higher field, you will get a slow exchange regime. Okay, sometimes this helps, sometimes it complicates. You will see that you probably getting a good line peak shape in a lower field machine. But you go to a high field, you will see that your peaks are becoming broad. Because in the low field, they were in the slow exchange regime. Now you are putting them into intermediate exchange regime. So it becomes broad. So these are the things you have to remember. Okay. Now, how do we know that there is a dynamic process happening in a sample? So if the NMR spectrum exhibits a reversible changes as the sample temperature is varied, you can tell that yes, there is a dynamic process involved. So what you do, you record the NMR at a particular temperature, increase or decrease the temperature. If you see there is a change in the NMR spectra, and then again you It is only one, not only one direction. You again return back to the same direction, and if you see the same changes are happening, then you will say it's a dynamic process. But suppose you have done increase the temperature, and then when you are reducing the temperature, you are not able to see something. Probably some reaction must have happened. Okay, so that's why you have to see in both the direction. When you do this experiment, you first increase the temperature incrementally, let's say by 5 degree or 10 degree, and then you record the spectra. And then again you cool the sample and again see that whether you are getting back the same thing, whether what you did with the increasing the temperature. So if you want to study a dynamic NMR process by NMR, then you have to do the following things. First thing is that you have to determine the values, the chemical shift values of the two group of nuclei, nu and nu B. And then there are fractions of the molecular population that I also told you. So there may be one, most of the time you will see it will be, they will not be equal. Okay, okay, depends on what structure you are dealing. Okay, like case of ethanol complexation, it will never be 50-50. There will be a variation, and there is a less chance of becoming 50-50, but DMF will be always 50-50. Okay, then you record the spectra. So you have to find out, and that can be found out from the integration of these peaks. Okay. Then record spectra at various high temperature, including the coalescence and into fast exchange regime. So you have to keep on increasing until unless you from slow regime to fast exchange you are getting, and then also you have to see the line width in the fast exchange limit, because you will get the delta from here to put in your line shape equation, and then you should pull the sample, okay, and see whether you are again getting all those things. What I have told you, same thing is written here. So now how to utilize this information to find out the activation parameters. Okay, so as I told you, in case of DMF, the activation energy is very high, about 20 kilocalorie per mole. Okay, so how we calculate those activation parameters? So if you want to find out the activation parameters, you have to use the Eyring equation of transition state theory. And all of you must have studied this thing in chemical kinetics. What is Eyring equation? So rate constant is equal to kappa into this Boltzmann constant Kb. This is the temperature, and this is the Planck's constant. Okay, this is your delta G dagger is your free energy activation, free energy of activation, and RT are the universal gas constant and temperature. And if you rearrange this equation in this form, so put the values, I have given you the values of kappa is normally considered to be unity. Normally kappa is taken as 1, and if you take that and put all these constant values, you get an equation. The del G dagger is equal to RT into 23.76 minus ln K by T, and now you can split delta G into delta H, and so enthalpy and entropy, same thing has been done. And if you rearrange the equation, it becomes ln K by T is equal to 23.76 minus delta H dagger by RT plus delta S dagger by R. And if you plot ln by KT versus 1 by T, what you will get is a you will see a plot with negative slope that will give you delta H dagger by R, and this intercept is your 23.76 plus delta S dagger by R. So this is a standard thing. This is the way. So automatically, if you find out the rate constant, what the way the experiments I said, and then you can find out the activation parameters. Okay. Now let us see the there is also another relation, the relation of rate constant at the coalescence temperature. Now this coalescence temperature is a temperature where you will see both the peaks now lose their identity, so they become very broad. Okay, and one can calculate that when you take two equally populated sites and if you apply this to the line set equation, then K, the rate constant at coalescence temperature, is equal to pi delta nu. Delta nu is the difference between the chemical structure of the two sides divided by root 2 and nothing but 2.22 delta nu. Okay. And then from that also you can find out. So if you know this, so that's why when you record a NMR, actually people try to find out at what temperature the peaks are just losing their identity and becoming very broad. So that is the temperature of coalescence. So if you know that, you will be able to very quickly find out the delta G dagger, okay, the activation energy, okay, for this. And if you know the activation energy, you can find out the rate constant. So if you know the rate constant, you can find out these parameters, or other way around, from the recording the spectra, you can find out the coalescence temperature, and that is the relation. So delta G dagger is equal to R. This is the temperature of coalescence, and this is that same the constant which you are coming from the various constants, and then this is ln. This is your again coalescence temperature, and this is nothing but delta nu. Okay. So one can find out. So these are the ways you can find out the parameters. Okay, so now we'll see that some practical examples. So those are the things which are mostly done the calculations based on the when the two sites are equally populated. Okay, but you will see that I told you the host guest complexation interaction. So there you may not get 1:1. Okay, so let us see what kind of information we can extract from this kind of study. So again, now we have taken the same example. The ethanol is complexing with its receptor. Okay, so let us say this is your host. This is the guest, host, and this is guest. So this is host, this is guest, and this is the complex. Sorry. So this is your host. This I will call. This is a sorry. This is guest, this is your complex, this is your host. Okay, so they are in equilibrium. Okay, so you can you can very easily write the what will be the equilibrium constant. Equilibrium constant, you can express them in terms of rate constant and also their individual concentration, and also from there you can go to their mole fractions. Okay, so that only I have given. Finally, it is the mole fraction of the complex divided by mole fraction of 1 minus mole fraction of complex, that is nothing but the mole fraction of the host and the concentration of the gas. Okay, so now we'll go a little more ahead. So this is the thing I have already told you. Now there are two possibilities. One possibility is the slow exchange, another is the fast exchange. Let us see what happens under the slow exchange. Okay, we'll see that. So suppose we want to study this under slow exchange. So what is the requirement? See, all system cannot be studied. So what is the requirement that it can be studied? So the requirement is that at least one nucleus in the uncomplexed host, okay, or uncomplexed gas must give rise to a signal whose chemical shift we call that delta H is related to the, or I will call this is the nu H, I will call nu G, okay, or delta H or delta G, whatever way, okay, is significantly different from the same nucleus in the complex. I mean to say, if you see this example, when it is complex, the chemical shift of this methyl should be different from this. That is the only thing I wanted to take. Okay, same thing has been written in the language. Okay, so then del delta is nothing but the difference between the host and the complex. Okay, so and then you can modify the equation now. So this will be now we'll change this. What will be the concentration of host? So host you will be taking, see host, you cannot measure the host, no? So automatically you have taken some amount of host at the beginning, and a part of that has been formed complex. So that is nothing but the equilibrium concentration of that. Similarly for the guest also. Okay, and then these are the pre-complexation concentration. Okay, and how we'll find out that fractions? So you can find out the fraction of the complex is the, you have to take the integration of the peak due to the complex divided by the integration of the complex as well as the host. So that will give you the fraction. What is XC? XC is automatically the whatever is coming from the signal, whatever is complex divided by what is the total. Molarity you have to see, or mole fractions you have to see. So there, that you are doing correlating with the intensity of or integration of the peaks. Okay, and then if you do all these modifications, you get a equation like this: K is equal to fraction, mole fraction of complex divided by the pre-complexation concentration of the host into 1 minus same thing, and then R minus Xc. R is nothing again, the pre-complexation concentration ratio of G0 and H0. Okay. So now if you do that, so this is your, so you got these things you got from your when the process is slow or under slow. We want to find out this thing in under fast exchange regime, or let us see how we can utilize this. So these informations you got from the slow exchange regime. Let us see what information we can get from fast exchange regime. So under fast exchange conditions, the observed chemical shift, so you will get a chemical shift. That chemical shift will be a weighted average of the chemical shift of the host and the complex. Okay, that only I have shown here. Okay, and from there also you are getting XC. See, now ultimately if you want to get, see, finding out the mole fraction of XC is not so simple. Okay, so see, now you can find out the XC by from the chemical shift values. So you know the chemical shift delta H is very easy to, you can find out the delta H, the host, you take the pure host, record the NMR. Okay, and this this delta is the when there is a complex in the fast exchange regime, you are getting the delta value. That is also a measurable quantity. And this del delta, what is the del delta? Del delta is the chemical shift difference between the chemical shift difference between the host and the complex. So that you are getting from the slow exchange regime. Okay, so you get the XC. Okay, now let us see how we can find. This is one equation and this is second equation. And if you do a mathematical manipulation, you get a equation this. Okay, this is as I'll give you this as a assignment. How this if you use these two equations, automatically you have to take the parameters, what is Xc, what is del delta, and how you get this, that you have to derive. So finally you will see that you will have a, so when you measure, you will get a delta value, and you are having a R is equal to, that is G0 by H0. Okay. Okay. So what you will do, you will plot a delta versus R. So delta you will be getting, and R you can change. You can change the guest concentration. So if you keep on adding, so this is called the NMR titration. So what you do, you take your one sample of, let us say, keep the host concentration constant. Okay, and then you keep on changing the guest concentration. So your R value will be changing, and you measure the chemical shift, how the chemical shift is varying. Okay, and then you put those informations into this equation, and if you do a plotting of that, depending on the K value, let us say, okay, now I have shown you several plots. depending on the K value, how this is your delta, observed delta, and this is your R. You see, depending on the A value, as your R is changing, you see there is a very little change in A. But you see that G, F, and E, and D, there is a drastic change. So you see, if you see that in all cases, delta asymptotically approaches. So this is nothing. So this is your delta host, and this is your delta complex. Okay. So delta host is 0 and delta complex is 10. Okay. Now, if the K is large, you will see that when you give a small amount of gas, it will form a complex. So that's why very quickly it approaches the delta C. But when the K value is less, you see that they are not giving the proper value. Okay. So those things are only given here. Now, for such cases, you can keep on increasing. Okay. You will see that when R is equal to 100, okay, still you see that it is about when R is equal to 10, it is about 0.9% of the delta C. When it is 100, it is about 50% when R is equal to 100. Okay, so that's why if the complex, the equilibrium constant for the complex is less, okay, then you will see that you have to keep on increasing the gas concentration, okay, and you may not get a good result. Okay, so this is the way one can find out your all these parameters, and from these parameters you will get your equilibrium constant, and then the rate constant, and then the thermodynamic parameters. क्या हो गया? अरे just click on this line. Huh? Okay, so whatever I have told, there are also limitations. Okay, so if you see the equation, now the delta H and delta C must be known, but I have told that delta H is very easy to find out. You can take the pure host and measure the and record NMR, you will get the delta H. Okay, but delta C has to be measured. But you see, the delta C measurement is there is a big problem. As I told you, you have seen that first thing is that the rate constant. Okay, the rate constant for complexation and decomplexation are usually very large, making it possible to reach the slow exchange limit. Okay, that's why see these kind of complexations are very fast. So if you are not able to reach the slow exchange limit, you will not be able to find out the delta C. So if it is a slow, you will get two peaks, one due to the complex, one due to the host. But if it is fast, you will get a average peak. But for host, it is easy because host is a pure material. You can record it separately. But you do not have a pure complex in your hand. Okay. So then I told you that if the K is if it is K is large, then only you can approach the delta C limit. If you see the earlier plots, you see if your K is, when K is let us say E is equal to 5. So when K is more than 10, you will see that you can get the very close to the delta. Still it is not delta C value, but it is very close to delta C. Okay. Okay, so that's why the thing is that the delta C limit, it is not very easy to reach with a reasonable value of R. So now you have two unknown parameters. You have the equilibrium constant and the chemical shift value of the complex. So so in this case, you use a non-linear curve fitting to determine which values of K and delta C best simulate an experimental set of delta versus R. So you have to do some kind of simulation to see which delta C is best. You have to change the delta C value, okay, and K value, and see which where you are getting the best fit for the curve. The other limitation of this method is that, see, what are the assumptions we have made during deriving these equations. One thing is the delta H and delta C are independent of temperature. It is not like that, okay, and concentration effect. So those things are not being considered even in deriving all these whatever equations I have said. Okay, so if there is a significant difference in effect of temperature and concentration, then you may get a wrong result. And then you see, as large range of concentrations are used, okay, equilibrium concentrations may not depict the correct equilibrium expression because we are using the concentration term. Okay, so if we know that if you use a large concentration, then you have to use the activity and activity coefficients. So those are the things will come into picture when you go for the higher concentration, and that happens when your equilibrium constant value is low. And third thing is that your processing of the data, as iterative non-linear curve fitting, it involves location of relatively shallow minimum. Okay, so that is a problem, and then that's why it can give you a significant error in your equilibrium constant claim. Okay. So the bottom line is that when an NMR spectrum exhibits a shift in delta as a function of concentration of other potential interacting species, this is probably due to complexation induced shift under fast exchange condition. So if you observe that, then you can qualitatively tell, you will means quantitatively you can find out those things, but still there will be errors. Okay. So I'll stop here. Next class, I will say qualitatively how you will tell whether what type of NMR experiments you should do to tell whether there is any exchange is happening, okay, or some kind of complexation equilibria is there or not. I will tell what are the NMR experiments to be done, okay. This is nothing a kind of your physical chemistry principles which can be used for deriving various parameters, okay, to tell something about the energetics and other things. But if you want to tell qualitatively, and as I told that there could be a lot of errors, but if you want to tell qualitatively, I will tell in the next class what are the experiments you should do to tell that yes, there is a exchange is happening, okay. So I'll stop here.
Okay, you will announce one thing. This announcement for exam will be circulated soon.
Okay, now you just see your class will be over in next week. Next week there will be 2 classes and you will have a class on Friday. So now there will be 3 more classes. So
this part 1, part
yes. So part 1, all these things, the whatever is there in the part 1 of NMR advanced NMR spectroscopy course will be covered in this by next week, okay. And we'll be announcing the exam date soon, and also
those is already decided. So registration will be,
and we will put who will be eligible for registration, okay. So that will be solely decided on the basis of who have submitted the assignments as well as who have attended, depending on your attendance, as attendance percentage. We will put those names, okay.
So if you want to, hello participants, if you would like to attend this exam, then please submit your assignments as early as possible. We are still keeping it open. So submit your assignments as early as possible, because the assignment carries a marks, and we'll put a criteria for submitting assignments for eligibility in sitting for the exam. So please remember that. And attendance part, anyway, you cannot change one now. But there will be a cutoff depending on the attendance. So this eligible list of eligible candidates will be circulated to you. So who are eligible will be communicated to them only. Okay.
And then you can register for exam, and you and those who will be eligible appearing exam, they must submit the assignments. Okay, it is must, otherwise it carries a mark. Okay, it will be difficult for them to pass until unless those submitting the assignments. So I will give you one assignment maybe on Monday or Tuesday next week. So by Monday only we will circulate that. Okay, and then we'll put the deadline also by which date you have to submit all assignments. Okay, so if you have any doubt, I will advise that you please go through all the lectures. You write down the lecture numbers and the lecturer's name, and you must, if you have any doubt, you must send one email, so that because then only you will get your response. You have to tell the lecture number. Okay, and then we'll communicate to the respective lecturers, and they will clear your doubt.
Okay, participants, all the best then. So next week we'll be completing this part 1 course.
And Friday you will have class from 4 to 5. This Friday also you will have class from 4 to 5.
Friday, and maybe
I'll continue with the dynamic NMR spectroscopy.
next week 2 classes, right?
Yeah.
Most likely. Okay. Thank you very much.